Today our topic is to talk about photometry, which is the measuring of how bright things are in the sky. And this is also my opportunity to tell you a little bit about my own research, which is involving doing photometry of objects in the outer solar system, particularly Pluto and also a Kuiper Belt object named MU69 that the New Horizons probe, which visited Pluto a couple years ago, is heading towards. So what is photometry? I've already mentioned briefly is measuring the brightness of a light source. In astronomy, typically we're talking about stars or galaxies or some other astronomical object. If you measure an object's brightness repeatedly over time, you can graph it as what's called a light curve, which is a graph of brightness on the vertical axis and on the horizontal axis time. And if the object is changing in brightness, you'll see fluctuations. If the object doesn't change in brightness, it would just be a horizontal line. But if it changes, it'll dip, it'll move. So for some purposes, the brightness measurements must be absolute. That is, they have to be calibrated. So the brightness is measured in defined SI units, like watts per square meter or apparent magnitude. In other cases, the measurements can be just relative. That is, you don't really care about how bright the object is, but you do want to know that its brightness dropped 15% for a certain period of time. And so you don't necessarily have to calibrate, but you do have to at least have some kind of arbitrary measurements. So you can say what percentage it dropped for how long. So for some examples, here are the light curves of two variable stars. A variable star is one whose brightness changes. Our own sun basically is not a variable star. There are tiny, tiny, tiny fluctuations as sunspots come and go, but we do not consider the sun, our star, to be a variable star. But there are many, many stars in the sky that do change their brightness dramatically on varying timescales for varying reasons. So some of those reasons are intrinsic. That is, the star itself is pulsating. The star is either getting bigger and smaller, or it's getting hotter and cooler. Maybe it's doing more than one of those. But the star is actually changing its brightness. Other stars change their brightness not because the star itself is doing something, but because something outside the star is blocking the light. So the second graph here in the lower right is an eclipsing binary star, that it is two stars that are orbiting each other. And from our viewpoint, I'll line up with the camera, from our viewpoint, one star passes in front of the other. So when they're like this, you see both stars. But by the way, I need to say, we're not resolving these stars to our view through the telescope. It just looks like a single dot. But they're really two objects orbiting each other. And so when they're like this, you're getting the light from both stars, but when they're like this, one of the stars' light is blocked, and then half an orbit later, the light from the other one is blocked. And that's what's going on here. The one star is blocked, and then the second star is blocked, and then it repeats over and over again. So this is what's called an eclipsing binary star. It's an extrinsic reason for the variation in the brightness. Whereas this one right here is an RR Lyra variable star. It's a single star whose brightness is actually changing over the time scale of about half a day. Here's a light curve of a supernova. A supernova is a star more massive than the sun. Stars derive their energy from nuclear fusion of hydrogen in their cores, but as time goes on, they're using up that hydrogen. When they run out of hydrogen in the core, a variety of things can happen. And for the most massive stars, they end up exploding in a supernova. The result you get, the remnant you get, is a neutron star or a black hole. Now, this particular supernova is a kind of supernova where you get an explosion, but it's delayed. The star is actually not massive enough to immediately explode, but rather becomes what's called a white dwarf, and after it runs out of fuel. becomes a white dwarf. This is what our sun is going to do in about 5 billion years. It's going to become a white dwarf. But if that white dwarf is itself in a binary system, that is, there's another star, and that other star runs out of fuel, it will expand and become what's called a red giant, and mass from that second star will get transferred onto the white dwarf until the mass builds up enough that it explodes in a supernova. And that is what this graph is. All the dots are the actual measurements, and the line that runs through them is kind of a model fit to the curves, kind of like a best fit line, only it's not straight. Here is a light curve of a transiting exoplanet. Sorry, I'm chopping off the title there, but that's exoplanet. An exoplanet is a planet that's orbiting a star other than the sun. And until 30 years ago, the number of known exoplanets was 0. Now the count is several thousand and growing rapidly. Most of these have been discovered using photometry. Keep in mind that the planet itself is too faint and too close to its star, its sun, for us to see directly. And so from our vantage point, it just looks like a star. But every once in a while, the star's brightness dips. And that's because, kind of like an eclipsing binary star, where the planet has passed in front of the star, as shown in the animation in the lower right. So the planet is moving in front of the star. It's blocking a small percentage. In an eclipsing binary, it can be a large percentage. For a planet orbiting a star, typically it's much smaller than the star itself. The dip in brightness, percentage-wise, is quite low. So this is tricky to do. But like I said, we now know of a couple thousand stars discovered by stars that have planets discovered by this technique. So my own research involves doing photometry of Kuiper belt objects, occulting background stars. So the Kuiper belt is the disk of material outside Neptune's orbit in our solar system. And here are some pictures. So in the upper left is the body of a comet. This thing's a couple miles across. It's outgassing because it's near the sun. And from a distance, the object looks like this. This is not the same comet. This is a different comet. But when these big mountains of icebergs come in close to the sun, they outgas. The gas gets pushed backwards away from the sun by the pressure of the sunlight, forming a tail, and that's a comet. And most comets come from the far reaches of the solar system. They only come to the inner solar system briefly. And so the Kuiper belt is one of the repositories of comets. And in the lower right, I've started an animation just to show you. This is actually one of the largest Kuiper belt objects. It's roughly the size of Pluto. It's called Sedna, and it's just a dot in the telescope. So it's hard to measure the size of something that is just a dot. So my own work recently has been involved doing photometry of a Kuiper belt object much fainter than Sedna. In fact, so faint that the only telescope that has seen it is the Hubble Space Telescope. This object, MU69, is nonetheless, it is the target for New Horizons. The probe that flew by Pluto a couple years ago is going to pass by MU69 on January 1st of 2019. Here's a quick little, just a diagram showing you the Kuiper belt and the path of the New Horizons probe that launched from Earth in 2006, past the orbits of these other planets, and passed by Pluto almost 3 years ago in 2015 in July. And it is now almost at MU69. So what we do for this research is we make predictions. We make predictions of the motion of MU69 or other objects like Pluto or other KBOs. And from the perspective of the Earth, we predict where a shadow will pass as that object passes in front of a background star. So last year, for instance, there were 3 occultations by MU69. On June 3rd, the shadow passed over South America and South Africa. In July, passed over the Southern Pacific. And July 17th, sorry, the date is cut off, passed over the extreme southern end of South America. So I was in South Africa for the June 3rd occultation, and this is where we deployed telescopes. So what we do is we deploy small telescopes. We had some near the coast, we had some inland to avoid a possible weather system, because if it's cloudy, when the shadow passes, if it's cloudy, there are no redos. You can't do it over or reschedule. Here's a pretty picture of one of the telescopes set up. That's the Milky Way crossing the sky. If you're in the southern hemisphere and far from city lights, the view is just amazing. And here is an actual occultation. This is one, this particular video is from the July 17th in August, that event when MU69 passed in front of a star. So we're not actually measuring the brightness of MU69. We're measuring the brightness of a background star that's way, way off in the distance, much fainter than you can see with your naked eye, but visible in what are actually fairly small telescopes. These were 16-inch telescopes we were using, 16 inches in diameter. So if you look at that video, you can see that the star in the middle blinks out, and it blinks out for about 1 second, approximately. And so we travel all over the world in order to get this star blinking out for 1 second. But the exact time and exactly where on the Earth it blinks out gives us really valuable information about the size and the shape of MU69. And that's important because New Horizons, when it arrives, it's not going to be controlled from the ground. It's just too long for radio signals to go back and forth. So New Horizons is going to be pre-programmed for its flyby of MU69. So the program is going to aim cameras, it's going to open shutters, it's going to be taking measurements, and the programmers who are running the probe need to know how bright, like the surface brightness, is MU69, is it like dark like a piece of charcoal, is it bright like a snowball? Knowing what's called the albedo, the brightness of the surface, is really important, say for determining the shutter times on camera exposures, for instance. So it's really important for us to get this information to determine the size and brightness and albedo of MU69. There is another occultation coming up on August 4th, and we are deploying to Senegal and to Colombia to observe that event, the last opportunity to get detailed information about MU69 before New Horizons arrives there. So here's just a pretty artist conception based on the data from last summer's occultations. It looks like MU69 is either a very elongated, like stretched out potato shape, or might actually be a close binary object, where you have a moon, but rather than thinking of it as a moon, it's really better to think of it as a binary object that's very, very close. And so it's going to be really interesting either way when New Horizons arrives on January 1st next year.